All right, we're running. Hi, Miss Carol.
Hi.
This is my ICP class, morning ICP class.
Good morning.
Good morning. Good morning. They're hiding from you. No, they're great students. Okay, and I just handed them a guided notes packet on electrical circuits. All right. Now I know we've already kind of touched on batteries. We really didn't kind of define them. We may have even already written some of this when we started our circuit lab. But the cell is another name for the battery. When there's a battery that has a positive and a negative side, then it is a cell. And the cell stores the chemical energy and transfers it to electrical energy when a circuit is connected. So remember when I put the battery inside that box, and then I connected it with the wire to the light? Light lit. If I didn't put the battery in the box, there would be no electricity going through the wire. A 10 from the East German judge, right? I stuck the landing. All right. When two or more cells are connected together, we call it a battery. And if you look at a battery, you say, but there's only one battery. Well, there's two cells in your battery. There's a cathode end and an anode end. So there's two different generators of ions inside one battery. And this chemical energy that's inside this battery is used up pushing current around the circuit. That's why a battery either needs to be recharged or it dies and you have to throw it out, right? So does anybody have rechargeable batteries that they use in something besides your sweat?
I use them in my controllers for like my gaming systems, like the guns.
So your game systems, controls, that's a great, does it last a long time?
Cameras.
Digital camera?
You need it for your phone? You charge your phone?
Yeah, your phone battery is a rechargeable one, but you usually get that. You don't buy it separate. You know, doesn't it usually come with a recharger? At least mine does.
Yeah.
And the battery's not really, doesn't really look the same. But you can buy batteries like that that are rechargeable, and she uses them in her remotes for her games.
You save a lot of money.
Huh?
You save a lot of money.
Did you hear? You save a lot of money. Because, and you also help the environment because you're not throwing away those wasted batteries. Okay, now when I started listening to music a lot, when CDs came out and I didn't have to drag around a big old record player, I used AA batteries like they were orange juice all the time. So I went through a lot. But I should have gotten batteries that recharged, and then I wouldn't have wasted so many going through them. Because they went fast.
Yeah.
Okay? All right. Does everybody have their blanks filled in for that one?
Yep.
Okay. All right. Now, I may not have put this since you guys already know about the electric current, but an electric current is a flow of microscopic particles called electrons. You already know what an electron is. Flowing through wires and components. All right, this is a word we may have not touched on yet. Component. What in the world is a component? When I had the little battery case and the little light bulb and the wires, what are the components?
It has to be like something similar to a joint, like something like say
Joining it together?
Yeah, like
so like a what? Like a light bulb or? Yeah, that's a component. A light bulb is a component because the electricity is going to run through it. Sometimes we put little chips and stuff in between. What else would be a component? How about anything you plug in to the circuit, right, is a component. So if you have a stereo, we call the speaker and your woofer and your tweeter and all those the components of your stereo, the parts. Okay? Does that make sense? So which way is the current flowing in this? From negative to positive or positive to negative?
Negative to positive.
That's the way the current will flow. through a cell or a battery from negative in to positive. Now, is there only 2 electrons in a circuit? No. There's millions and millions. So, now, this right here is kind of a little symbol, and I'll give you a copy of what these symbols mean for a battery. Nobody wants to draw a complete battery when they're trying to draw a circuit. So this is kind of like shorthand for electricians. And that's a battery. And it's always going to mean a battery. You know how we have those symbols on the highway? And we know that a little tow truck, with this through it, means no parking there or you're going to get towed. Well, this is a symbol that you can understand, that everybody understands, for battery in a circuit or cell. Okay? Make sense? Like, all right, it asks you. All right, here's a circuit, and I think I gave you that picture. It has a cell. Keela, which part of the circuit is the cell?
The battery.
It also has a switch. Like this. Switch to open and close, right? You guys love when I do stuff like that, don't you? And in this circuit, we have a lamp. One of our components is a lamp. Do we always have to have a lamp in a circuit? No, it's just an easy way for us to tell if it's working. And then, of course, wires. Now, what has to be special about the wires to make the electrons move through them? It has to be a metal. And what property of the metal? I'm pulling on your
Copper.
Well, copper is good, but what does copper do that maybe not plastic doesn't do? It conducts. It's a conductor. Most metals conduct. And in this case, it's copper. It's a very good conductor. And it says to make the circuits, these components are hooked together. If they're not hooked together with the conductor, there won't be a circuit. The electrons won't flow. There's nowhere for them to loop. They can't get back to the positive end of their cell, right? They would just go this far if this green wire wasn't there, and it would stop because the electrons can't return to the cell. Got it? Did you, were you able to name your components? I did that drawing with the lines, and mine is a little bit different than yours up there. No, I didn't do the picture, but I did the lines, the little arrows, and I might have not done them exactly like they are up here. No, the picture was already done. Somebody did that for us. All right. When the switch is closed, the lamp lights up. So I am closing the loop. Sorry about that. I just wanted to show you what I was doing. So this is a closed switch. Kind of opposite what you would think. Closing usually means finishing. But I'm closing the circuit, so I'm allowing electrons to flow through our lights up here. And in this case, this switch completes the circuit so the electrons can make that loop pattern. So it says when the switch is closed, the lamp lights up. This is because there is a continuous path of metal for the electric current to flow around. So there's the metal wire, goes into the bulb. Bulb has that little wire filament. Comes out this wire, goes through the switch when it's closed, and back to the positive end of the cell. If there were any breaks in the circuit, the current would not flow. So when I open the switch, the current stops. Make sense? So interesting. Electricity. You know, like I said, we just plug it in and hope it works. Okay. Now I told you this, I don't know if I put that on your guided notes, but because I have actually all the symbols on a packet for you, you do not have to draw these. But I told you they have symbols for different things, so they don't have to draw a battery, a light bulb, and a switch when they're trying to draw a circuit. And I told you that means the cell, that one's the switch, and this is the lamp, the X. Alright, and then of course the lines are the wires. And I do have a packet for you to have that. Let me go ahead and hand that out, because then it might, I just don't want to confuse everybody. It's got a chart of those symbols. There you go.
Thank you.
Now, if I was going to compare this circuit to a water pipe and a water faucet, and try to use that as an analogy, what would the switch be that lets the water in and out? What would it? It would be the faucet, the valve. All right? And the wires, what would they be like? Pipes. So if you can think about water going through pipes and turning on and off, you can see how the flow of electricity is very similar to the water. Okay? And I think this thing I just handed out gives you those analogies. Right, and here's the symbols. You do not have to copy these down. But you've got a cell, a double cell, switch, lamp. I don't know what that one is. Resistor maybe? This is an amp meter, voltmeter. And this is a resistor. And this is an off resistor. We'll talk about what those do. If I turn the water on the faucet, it's flowing out, and I don't turn it all the way shut. What happens to the flow of the water? It still comes, but it's slowed down. That's what a resistor does in a circuit. Oh, there we go. That's motor. M is for motor. And buzzer. That's what that little thing looks like. It's got legs on it. All right, there are two types of circuits. This is back on your guided note. There's series and parallel. In a series circuit, right here, series circuit, the components are connected into and one after the other. So we've got the wire coming into this lamp, across its filament, out, back into the second lamp, and back around to its positive end. They make a simple loop for the current to flow around. So there's nothing fancy, it just goes around a little loop. If I take out this ball bar, it blows, the circuit is broken. In a series circuit, the circuit is broken because there's not that continuous flow of electrons. I took it out. Now, that's very frustrating in Christmas lights, isn't it? Mm-hmm. When you have one that pops and then they all pop out. Now, they've changed those over the years because when I was a little girl, they all did that. Now, they've got them in parallel so that you can have one out and the rest go, right? And this is a parallel circuit. The components are connected side by side, and in this case it's two lamps. The current has a choice of routes. I can go this way without going through that bulb and around, or I can go this way. Make sense? The components are connected side by side. The current has a choice of routes. Now, does the electron, the current, the electron flow really choose? No, it doesn't have those kind of reasoning. It's going to go the path of least resistance or the path that is the strongest. And if I take one of those out, it will just stop using that path and use this one. Okay? If one bulb blows, there is still a complete circuit to the other bulb to stay alive. Not so frustrating for Christmas lights anymore. Now, if you pull out the light bulb in most Christmas lights, sometimes that'll make them all go out because then you don't even have the connection there. But if the filament is blown, you can still have the parallel circuit. What do you think about your light switches at home? Think that they're parallel or are they series?
Series.
Does one of your light bulbs go out, they all go out?
No, parallel.
They're parallel, yeah. So that's why you kind of have if you've ever watched someone take the light switch off, next time if you have an electrician in your house or your landlord or something, pull that out, look at it, because it's very interesting how that light switch works.
I got some stupid electrical outlets in my house.
They're stupid?
Yeah, because I have like this one radiator here. I swear, because like I drag it all around the house or whatever.
You drag around your
Yeah,
radiator.
you know how it has like the two buttons like you can, for the heat thing, you need to turn off one or both.
Right.
If I have both of them on, I swear to God, I turn on my microwave. It blows a few.
Probably because it's in the same circuit.
Circuit.
Okay, what is a fuse? That's something I haven't heard in a long time. What is a
A
fuse?
fuse is when they are located in different circuits, right?
Yeah.
And it's
We
like,
put the fuse in the
like-
circuit.
and then like one control like the upstairs, or one control like the kitchen or the laundry part.
Yeah, a fuse is placed inside one of your parallel circuits to protect the things that you plug in, or protect your entire
Fuse
house
box.
from your fuse box. All right. So if you use fuses, the kind that screw in, is that what you use?
No, or
I just
switches.
go down in the basement and just have
Yeah, the switch.
Switch.
Okay,
Yeah.
that is called a breaker.
Yeah, the breaker.
Breakers have replaced fuses in most homes. Now, my first home in Noblesville, hasn't been that long ago, I had a fuse box. Before I sold it, they made me change that to a circuit breaker. Breakers do the same thing, except rather than blow and make the circuit stop, the flow, they actually just turn off or open like this. They actually
So you turn everything. Well,
so it turns it off.
turn everything off.
It breaks the circuit. So whatever's in the circuit with that particular switch, you might have your oven and one light in your kitchen and one plug in your kitchen in the same parallel circuit. Alright? That's why it's very frustrating when you have to go flip the circuit for the microwave and you drag the heater to the plug. Now the plug isn't stupid. The plug is just you need to talk to someone to make sure that the amperage is right coming out of that plug. Microwaves and heating things like to pull a lot of current to work, okay? So that might be something you want. It shouldn't happen as long as your microwave and they're all set right. You shouldn't do that because it's parallel circuit.
So those are in part more than
Correct. Breakers, but actually most homes have breakers now. That you open it up and there's a bunch of switches rather than a fuse. Works the same way. They're just safer. Then you don't have to take them out and go buy a fuse and put them back in. Yeah, I had round ugly things. When we sold my mother's home, she never had gone to breakers. When I sold my little home in Noblesville, I had to go to breakers. It didn't bother us because we never, I guess, blew any. You ever watch the Christmas Story? And the father is putting all those electrical plugs on the tree and he keeps blowing fuses. That's not a good thing to do. If your fuses blow continually, you have an electrical problem that you have to check out. Yeah, definitely.
It's like in your cars too, right?
Yes, you have in your cars, at least in my car, okay, the fuse kind of looks like this. Maybe like a horseshoe in a way. And it's got a little, these are silver that plug in, and these might be blue, green, red, depending on what they are. And they work the same way. Huh?
fuse, like the old kilo truck, if you put the car in reverse, like the fuse will turn it on the turn signal, that fuse will blow.
Okay, he's got a short somewhere.
Yeah.
Okay, he needs, because something is shorting out, something is interfering with the flow of his electrons. Not, and so the fuse is saying, hey, maybe there's a wire.
He just takes it out.
Okay, tell him that the wire that controls that fuse, there might be a wire that's close to his gear shift that he's pulling out or something. All right, whoa. Oh, I don't like that. I'm very sorry. I thought I changed all those to white. Let me fix this so you can see it. Technology. Can't live with it, can't destroy it, right? And I apologize. I thought I turned this last night. Got tired. IXL tired me out. Okay, here we go. DC versus AC. Bam. AC/DC is a rock band. That's not what we're talking about here. DC is direct current. That's what that stands for. Okay, and where did I say we got direct current from?
From the circuit.
And the wires are in, the wires carry it, but where does the current come from? What starts it?
The electrons.
Electrons are moving. Where do they come from?
From battery.
From the battery or the cell. So if you have a cell or a battery, you have direct current. The electrons are flowing constantly, so they're going from the negative end to the positive end, so they're flowing constantly, like running water. Electrons only flow in one direction, negative to positive, which is what we've already talked about. And batteries provide DC current, direct current. So if you ever see that DC now, you can explain what it is. Trivia. What's DC stand for? No laughing. I'm taping this. Sorry, Miss Chen. We're having fun with this. All right. The current that is generated by either electromagnets or by turbines or whatever, and the stuff that comes out of your plug is called AC, alternating current. And when we did that Faraday computer simulation, you saw the electrons going like this, back and forth, back and forth. Hi. Hi. Wave to the camera. You're on right here. That, Miss Chen, that was my life coach partner. It's just for my mentor, James.
Who's never gonna forgive me?
So we call the pulse current because it kind of pulses, like your heartbeat, pulse, pulse. Your home electricity is alternating current. It's much more efficient for power transmissions over long distances. Why would that be? Why would we not put direct current through our wires? Huh? What? Well, if something is flowing clear from the power plant to the grid directly, yeah, it'd just be almost impossible to make sure that it's consistent all the way through, right? Or somebody doesn't break the current. So this pulse current, it's really, really more efficient. The USA uses 60 hertz, which is 60 cycles per second, of their alternating current. So the current, you saw that wave. We've done waves before. What does hertz measure?
What?
What does hertz? I know that I'm pulling on your old waves. Does it measure the
Oh,
height?
Height,
Nope.
no,
the length, like,
That's wavelength.
wavelength.
This is wavelength. This is amplitude.
Yeah,
What does hertz
amplitude.
measure? Frequency. Very good. Which is how many waves go past this fixed point. She is smart. You guys are all smart. That's why I want you to get your credits. And I want to be at your graduation. I want to be sitting on that stage going, yay! So we use 60 hertz, and other countries use 50. What do you think would cause us a problem if we went to France and they have 50 hertz and we have 60? What do you think might be a problem there?
We have to find adapters to use their electrical outlets because ours cannot fit.
Well, first of all, they don't fit physically, do they? Okay, you've got different frequency coming out of there. So what do you think else do you need? She said you need an adapter so that it'll fit. What about the electricity?
You can say that the USA is, we're using more electricity than them.
Well, we're using more frequency.
Frequency.
But if you have a hairdryer that you take with you to France, all right, and you plug it in, you got your nice adapter, you plug it in, and the power is different, what do you think's going to happen? Yeah, it's either not going to work or it's going to burn it up. So you also, not only the adapter, but you need a little bit of electrical transformer that will change it to 60 or to the voltage that you're putting in. So it's not just the shape, it's also the current. So don't go to Europe or any other country. I don't think Canada uses 50. But I don't know about anywhere else. I've been to Germany and I melted my hair with my curling iron. And why would I do that? Accidentally. I had my little adapter, but I did not have anything to change the voltage. So the frequency and the voltage were different, and my hair got too hot. There wasn't a fuse in my curling iron. I want you to know that my friends make so much fun of me. My co-workers never let me forget that. Why didn't I buy a transformer? I don't go to Germany very often. I forgot. I just bought what I thought I needed. Okay. Let's see what I got next. All right. It says electric current is measured in amps. And the letter we use is a capital A. And we use an ammeter connected in series to the circuit. So that means I'm pulling a little place out of the circuit and I'm sticking my ammeter in there so we can measure the flow across. Now, most people don't use ammeters. Most electricians. All right, they're minutes. What? They use voltmeters, and we'll talk about voltmeters. And I actually have a voltmeter to show you. You do not have to know how to draw an ammeter. But if you see an A, that means I've actually put the ammeter as part of my circuit. And that's how you would measure it in a series and a parallel. We're not done with that immediately. Okay. Next part is voltage. The electrical push, which the cell gives to the current, is called voltage. So the push that the battery gives it, of the electrons, going through, go, and come back to my positive end. Measured in volts using a voltmeter. Now you might have seen electricians and people that do electrical work, even people that take care of cars, they will have a voltmeter. My voltmeter right now is reading 0. Wonder why? Probably no electric current running through the air, right? Okay. So if I put a voltmeter, I use V in the circuit. You see that V, that means the voltmeter. Right. Okay, different cells produce different voltages, and then this starts your notes. The bigger the voltage supplied by the cell, the bigger the current. And unlike an ammeter, voltmeter is connected across the components. So I can hold this across the ends of the battery. I don't have to actually disrupt the circuit to measure the voltage across. Now you don't have to worry about potential differences at this point because we're not going there yet. All right, let me go ahead and flip the light on really quick. And I wanted to show you how to measure voltage in this little circuit, if I can make it work again. Here's a light bulb. So if I connect, if I connect my wires to the battery, which is another name for, what's the battery? Start with a C? A cell. Now you're going to hear that term used for a lot of different things. It's the little pieces of your body, okay, as a cell. It's where you're incarcerated in jail as a cell. And a battery is also a cell. So that word is used for many, many different things. Don't get them mixed up. So I'm making what kind of circuit am I going to make if I am putting the light bulb Let's mistake, sorry. Okay. What kind of circuit is this? Series or parallel? Series. Why, Deshaun? You don't know? It's the first thing that came to your head.
And in parallel, it can either go either way.
Right. Well, I would have a second wire coming out and hooked to another component. So the series circuit is just one continuous loop. Parallel circuit gives me different paths for the electrons to go. So this is a series circuit. Okay? So if I unplug the wires or I take out the bulb, it's going to not, the electrons won't flow anymore. So it says I can measure voltage across components. So I can either put it on the wires or on the little connectors of the light bulb. Now this light bulb doesn't let me get to its filament, so I can't measure on this particular light bulb across the filament because it's sealed up in the plastic. So if I take my voltmeter, and I put it across the components, in this case I'm going to put it across the light bulb component. I'm going to put it one coming in and one coming out. I'm getting about 0.01 volts. Not very strong, is it? One battery and one light bulb doesn't take a lot of energy to run it, but it doesn't push a lot of energy through. Now, take the same voltmeter, I'm gonna put it in here. Does anybody know how many volts I should be getting?
60.
Well, that's hertz, volts. What does it usually say on your electric equipment when you buy it? No, don't exceed blah 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 volts, because that's the limit of your plug. This is in your own house. Come on, guys.
50, you're like, I don't know.
Okay, can you read this?
100.
This one says 119. What is 119 pretty close to? An even number. 120. So your normal household current measures 120 volts. So can I run something that is a 110 on this? Yeah. Can I measure something that's a 240? No. Have you ever noticed that sometimes your refrigerator has its own plug, or your oven, if you have an electric oven, because the voltage needed to run it is greater than 110. So,
Happy birthday.
so that's how you measure voltage. So you know the voltage of your household current is 120, normal plugs. Now if it's not 120, or close, then you might have an electrical short or something going on. You might want to measure if that plug keeps blowing a fuse. But I wonder if your microwave needs more current.
I think it's just that house because I have another plug. If I plug up my iron, like, it makes one go back there.
Now it's the circuits that blow. So you put in your iron, which is the heating. And I will tell you that things that heat up can draw more current than something that just lights up. Because if I put a heater on this circuit, it's probably not going to do much. Not enough power going through, not enough current. All right, I'm going to go ahead and turn off my camera. I think she's got enough. Bye. Thank you guys for